Okay, so we're back, and hopefully all my rambling of the last video made some sort of intuitive sense. But basically, the universe cooled down enough to where we could finally start seeing light. It was the universe expanded enough, it became cool enough that light wasn't smashing into something consistently. That light could finally get out. It could travel a certain amount of distance before hitting something, and the universe was no longer opaque, that we could actually see it. Now, obviously, the early universe was still highly energetic, and a lot of the light that was being released would have been pretty energetic. It would have been very high energy light. But as that light traveled from wherever, and again, there isn't just the. It's kind of difficult to think about, to conceptualize, but the universe didn't just there's no center of the universe. There's, we can't look out and go, oh, okay, hey, if I shoot my telescope out here, I'll have to look in this direction. That's the center of the universe. The center of the universe was literally everywhere when the universe was first formed, and everything everywhere has been expanding since. So it doesn't. So it's not really. You can't really arbitrarily say where the center is, because everything has been expanding. Okay, be that as it may, we had these really high energy photons, really small wavelength, high energy rays, photons of light being emitted. And then as those photons travel toward us, well, of course, space itself has been expanding, and by the time those photons of light get to us, have gotten to us, they have been what we call red-shifted. Their wavelength is, because literally space is literally expanded. Those photons, those waves of light, now have a very long wavelength. They're very low energy, and we are detecting them in the form of microwaves, and this is what we call microwave background radiation. Well, the question that I would pose is, that's interesting. Energy can neither not be created nor destroyed, right? Well, as we understand it, this light that was emitted at the beginning of the universe, the early universe, lots of energy, right? Very small wavelength, lots of energy. We know that. And now that light has gotten to us, we have very long waving, very low energy. And the reason being is that space itself has expanded and is in essence, quote unquote, stretched the wavelength out and made it less energetic. So the question is, hey, where did all that energy go? You're telling me that the photon, when it was initially created or emitted, it had lots of energy. Now it doesn't have so much energy, and we're assuming that photon hasn't interacted with anything. It's managed to get to us without interacting with anything, and the only thing that has occurred is that space itself has expanded. Well, where did all that energy go? And to my knowledge, now again, I'm sure there are going to be plenty of physicists out there that are going to call me out on this. It could be my ignorance, but the way I look at it is, well, I don't really have a satisfactory explanation for where the energy. Maybe it's some weird virtual particle interaction. I don't know. All I know is that the whole energy conservation paradox seems to have been violated here. Well, while this is a great thing to think about, it does, I think, bring into clarity thermodynamics and what thermodynamics really looks at. But first of all, this is what we would call a large-scale issue here, the microwave background. Thermodynamics is not a science of looking at the universe. In a way it is, but really the essence of thermodynamics is looking at a part of the universe. Okay, you know, I'm here on my little Earth, and I'm in this room here, and I'm going to look at I'm going to make a system, and I'm going to look at, you know, maybe a little volume of space, you know, some gas in there perhaps, and that little volume is going to be my system. And that is really what thermodynamics deals with. Thermodynamics deals with systems. So when we apply the laws of thermodynamics, we need to be very careful about what we're talking about. And you know, as we talk about thermodynamics, I need you guys to that, you know, we need to be aware of that. We are taking a certain portion of the universe, a certain chunk of the universe, a small chunk, and it can be arbitrary, you know, obviously the size and whatever can be kind of arbitrary, but we choose it, and then we look at that chunk, you know, by itself, and we can do different things to that chunk. We can isolate it, for example. I can take the chunk, and I can say, hey, you know what I'm going to do is I'm going to take this system, and I'm going to isolate it from the universe. Maybe a thermos, for example, you know, where I have coffee inside of a thermos. And more or less, it's isolated from the universe around it, right? It's very well insulated, and I don't have a lot of movement of energy back and forth. Other systems are rather open. They're not as isolated. I have, you know, exchange of energy back and forth. So the way that I look at this whole energy business is that the conservation of energy applies to thermodynamics when we look at a system, and we have to be very careful about how we, you know, define a system, and there are, you know, very, very specific ways that we have to define it, and that perhaps thermodynamics doesn't have as much of an application when we look at issues like this, like, you know, the expansion of the universe and microwave background radiation. You know, thermodynamics plays a very specific role, I guess is what I'm trying to get at. And the role that it plays is in relation to taking systems, and, you know, often we have to put these boundary conditions in. So that's kind of how I get around, because there are, you know, other paradoxes that we, or, you know, not necessarily paradoxes, but other concepts that we can say, hey, you know, maybe the way that you describe energy being created and destroyed, you know, maybe you can, you know, I can get around this, and the whole point of thermodynamics isn't necessarily get around things, but thermodynamics is a very specific way that it's applied. And when we don't apply thermodynamics properly, I suppose, necessarily, then it actually does break down. It does break down. So basically, the whole point of the last couple of videos is we need to be very aware of what we're talking about with thermodynamics. We're talking about systems, and these systems, you know, are often isolated, or there's some sort of boundary condition that we place on the system so we can study it. And this will become even more apparent when we talk about things like entropy, and there are lots of different ways that people can conjure up to get around you know, entropy increasing in systems. And like, for one example, people could say, well, hey, look at the Earth. You know, the Earth is a system, is it not? And you know, hey, you know, there are lots of things going on the Earth, you know, where, you know, animals are making themselves, and, you know, DNA, and you know, it appears that, you know, the Earth is trying to be more orderly, and well, but look, the Earth is getting lots of energy from the sun, right? And, you know, the animals of the planet are using that energy, and, you know, making low entropy configurations. But in that process, you know, the Earth is giving off a lot of heat, and so on and so forth. So it's very difficult to look at the Earth as an isolated system, because it's not an isolated system. You know, it's got the sun, and, you know, all these other things going on. So that's where we need to be real careful about thermodynamics. Is we need to be very careful about defining our system. Okay, guys, as always, thanks for hanging in there.